All right, everybody, I think I'm going to go ahead and get started. Hello and welcome. I hope that you all are having a good week. Just about a month to go in the semester. I have a couple of quick announcements. First of all, I want to thank you all for the hard work you did on the homework that was turned in on Monday. I know there was a lot of problems there. People did a good job getting that in. And of course, I saw quite a few people in office hours, which is awesome to discuss some of that. But anyway, the good part about it is that actually there will be no more homework due this week. I actually decided to make your next homework not due until next Monday. So a little bit bigger assignment this week, but it's the only one we're turning in this week. Hey, so the next homework will be due on Monday. Part of the reason for that, and normally I would have a Friday assignment, but I actually am going to need to cancel my Friday office hours. So my Friday night office hours are canceled, but there's nothing due on Friday night at this point, so that's good. Instead, what I'm going to do, because I like to still have as much office hours as I can, I'm going to move them up a day. So just tomorrow. Tomorrow in the evening, 5:30 to 6:30, and then from 8:30 to 10. Of course, I also have pretty much the same hours today. So if anybody is trying to get an early start on the homework that's due on Monday, feel free to stop by either today or tomorrow. I will be a little hard to reach on Friday and Saturday. So just so you know, I should be back for my Sunday night office hours as well. So there'll be plenty of time to ask me questions as you're working on the next homework, which I don't think will be as long as the one that you just did for this past Monday. Okay. Does anybody have any questions logistics wise before we get into it today? Today's the day you've all been waiting for. Like, when are we ever going to see a differential equation again? Today's the day. So we're excited about that. We have a little bit of loose ends with linear algebra to wrap up. So the first half of the class, I'm going to do that. And then in the latter part of the class today, we are actually going to start chapter 8. And the last two chapters are about differential equations again, but with all of our linear algebra tools at our disposal. So it's the best part of Math 250B. I know you guys have been riveted already on the edge of your seats this whole semester. It's going to get even better as we get into these last 4 weeks or so. Right, so on Monday, we really hit this new idea about a non-defective matrix pretty hard. I want to come back to that again for a few minutes today. Remember that non-defective is just a synonym for diagonalizable. They mean the same thing. When I was a student, I got very confused by this. I was like, why would you have two words that mean exactly the same thing? But this is just the way the culture of linear algebra is. You sort of have to live with that. So we'll use either word. You'll hear me using them both interchangeably. What this means is that the matrix should have a full set of n linearly independent eigenvectors. Notice the n is the size of the matrix. So we have to have n linearly independent eigenvectors. In other words, every eigenvalue, quote unquote, pulls its weight. Okay, so this weight is, of course, generally referred to as the multiplicity. The multiplicity, guys, is the number of times that a particular lambda shows up when you factor the characteristic equation. So when you solve for your lambdas, you're going to want to write down repeats. If the same lambda comes up 2, 3, 4 times, you're going to want to write it down 2, 3, 4 times, right? However many times that is. Okay. So that's something to keep in mind. But every eigenvalue has to pull its weight. And what that means mathematically is that the dimension of each eigenspace, right? The dimension of each eigenspace matches the weight of that eigenvalue. Okay, so that's a perfect matchup between the dimension of the eigenspace and the multiplicity of the lambda. Does this make sense? What's over here on the right-hand side in black is just 3 different ways of saying the same thing. Okay. And linearly independent eigenvectors. Same thing as saying every eigenvalue pulls its weight. Same thing as saying that the dimension of each eigenspace matches the multiplicity of lambda. 3 different ways of saying the same thing. On Monday, we did this example that's in blue over here. And this is a good example of a non-defective, or in other words, a diagonalizable matrix. I'm not going to go through all the calculations again, but I've got a summary over here of what the highlights of the example are. This was the matrix I called B on Monday. And notice that the eigenvalues were 2, 2, and 4. Notice I'm writing the 2 down twice because I want to keep track of those repeats. Well, I then calculate each eigenspace for each of the lambdas and look at the bases. Look at the dimensions of these eigenspaces. Lambda equals 2 gives me a 2-dimensional eigenspace that matches the weight of the eigenvalue, which was 2. The other lambda is 4. It only shows up once, right? And since it only shows up once, then it has a one-dimensional eigenspace. So notice that every lambda is pulling its weight right here. In total, I have 3 linearly independent eigenvectors. That's what the thing on the top says. I have to have n linearly independent eigenvectors with each eigenvalue pulling its weight. Make sense? So this is just recapping that example from last time. Yeah, Jesus?
Will you, like, for a question, will you ever just ask us if it is non-defective, and then we just have to see if it does pull its weight, and then we don't have to check that one?
Right, I might just, exactly. So if I just ask you, is this matrix non-defective, and you pick one of your lambdas and find out that it doesn't pull its weight, you can stop. Pretty much game over at that point. It's not going to be diagonalizable. So this was actually, it relates, it's a good, I'm glad you brought that up, because it reminds me of something else I said on Monday, which is that if there are eigenvalues that repeat, you want to look at those first, because those are the lambdas that might not pull their weight. Look at my remark down here. Every eigenvalue will pull a weight of 1. So so the lambda of 4 right here, right? That lambda is going to give me 1 for sure, eigenvector. So I'm not worried about that guy pulling its weight. The eigenvalue that I'm worried about is the one that had a repeat. So I would probably, and I did this on Monday, I started with the lambda equals 2, and I did that one first, because that was the one that maybe would not pull its weight. Turned out it did pull its weight, but I didn't know that before I started. Is your question, Elias?
Yeah, you said last lecture, like let's say the 4 one, it can't compensate for the repeated one, right?
That's right, that's right. So the dream idea here would be that if one of my eigenvalues doesn't pull its weight, could maybe the other eigenvalue over pull its weight to make up for that? And what we said on Monday is that if you take Math 307, they'll talk to you about the fact that that cannot happen. So unfortunately, no eigenvalue will ever overpull whatever its weight is. And that means that as soon as one of your eigenvalues fails to pull its weight, it's game over. Not going to be diagonalizable. Clear so far? Yeah, so every eigenvalue can always pull a weight of 1. Any lambdas that don't repeat are safe. They for sure will not cause us any problems. And so I have this extra comment. I'm not sure I wrote this down on Monday, but I just made a point here that if the matrix does not have any repeats, then for sure it's diagonalizable. So if there are no repeat lambdas, then you already know that pretty much you win. It's going to be diagonalizable. Making sense? I want to make a point here for a moment, guys. When you just stare at a matrix randomly, you probably cannot tell most of the time. You can't just look at it and say, oh yeah, that's diagonalizable. You're not going to be able to do that. You have to get your hands on the lambdas, and you got to calculate these null spaces. You've got to find these eigenspaces. That's the only way you can really decide whether the eigenvalues are pulling their weight. It's just not easy to glance at a matrix and be able to answer, or be able to decide if it's diagonalizable or not. But there is one exception, and I want to take a minute and talk about constructing examples with you here, guys, because in some special cases, we can actually make some headway fairly quickly, right? Remember that to find the lambdas, you guys remember how to find the lambdas over here? What do? We do the determinant of
A minus identity.
A minus lambda I, right? And we set that equal to 0. We have to solve this equation, right? So a lot of times that takes some hard work. We have to do cofactor expansion, and then we have to do a bunch of algebra to kind of get it all factored out. We did that on those examples on Monday. But is there a particular type of matrix? Does anybody remember from back in the determinants chapter? Do you remember any kinds of matrices that have easy determinants to find, Josh? Triangular, right off the top of our heads, we've got that. Yes. So a quick note is that if the matrix is triangular, I can get the lambdas immediately. Let me show you why, right? So if A is triangular, that could be upper or lower. If A is triangular, then the eigenvalues of A are precisely the numbers on the main diagonal. So we can construct some examples where we can get the lambdas without a lot of work. So the eigenvalues of a triangular matrix are right down the main diagonal. Let me just to totally convince you of this, let's just do an example of that. Suppose that A is the matrix 1, 0, 0, 2, 3, 0, 4, 5, 6. This is a lower triangular matrix, right? This is an example of a lower triangular matrix. Suppose I want to find the lambdas. If I want to find the lambdas, right, I have to do the characteristic equation. This is where we subtract the lambda off of the main diagonal. So we just leave everything else the same, but we subtract lambda off of the main diagonal. And it's a lower triangular determinant that we're going to calculate right here. This is lower triangular, right? So this is simply 1 minus lambda times 3 minus lambda times 6 minus lambda. That's what you have right there. Just using the triangular formula. And now, with the characteristic equation, you're going to set that equal to 0. And so then you can get your lambdas. In fact, it's already staring right at you, 1, 3, and 6. And those are just the diagonal entries of the matrix. Does that make sense? So for a triangular matrix, getting the lambdas is suddenly easy. Yes.
This doesn't make it diagonalizable though, because you could have it 2, 2, and 2 for the diagonal.
We could have repeated lambdas on the diagonal, absolutely. But suppose I give you an example. Let's write this down. What if I ask you to write an example? Write an example of a 4 by 4 diagonalizable matrix. Let's see if we can, let me grab a different color here. We'll just see if we can write this down. So suppose I want to write down an example and I don't want to work very hard, right? I don't want to have to check a bunch of null spaces. I don't want to do any EROs. I want to keep my life very simple. And so what kind of a matrix? I know it's got to be 4 by 4, but what kind of 4 by 4 matrix do you suppose I might want to think about using?
Triangular.
A triangular one And, okay, maybe this time let's go with upper triangular just to mix it up a little bit. So I'll put some zeros below the main diagonal there in the lower left corner of the matrix. And what do I need to do with the number? If I want to guarantee that the matrix is diagonalizable, Matt, what should I do with the main diagonal?
They'll have to be different numbers.
Just pick 4 different numbers, right? Make sure that there are no repeats, right? If A has no repeat lambdas, then we already know that the matrix is diagonalizable. So you just take your 4 favorite numbers and you just write them down. So I don't know, 8, 6, 2, 7, whatever, right? So you pick those numbers and then you just, actually the rest of the matrix, to be honest with you, I don't even care what kind of numbers are up here. I'll just put little stars here to show that there's something up there, but it really doesn't matter. The point is, this matrix has lambda values of 8, 6, 2, and 7, and that means there are no repeats. And if there's no repeats, then my remark says, then the matrix is diagonalizable for sure. Okay? So there is if you're asked to construct examples of matrices that are diagonalizable, hopefully everybody's got the idea how to do that now. We just make something triangular and we just make sure that the numbers on the diagonal don't repeat. Now, if the numbers on the diagonal do repeat, would that mean that the matrix is not diagonalizable for sure?
Now you gotta check.
It wouldn't mean it for sure, would it? We would have to stop and check. If there are lambdas that repeat, then we have to see, well, maybe they still pull their weight, right? If they repeat, they still could pull their weight, but we'd have to check it, right? It wouldn't be as simple as this. That's why it's so nice to choose different numbers here. Well, guys, I think I've already given you enough ammunition to do the group work today. The thing I want to do in this group work is, so, you know, a diagonalizable matrix is a good thing. And I haven't really explained why. That's going to come in just a few minutes, but it's a good thing. Is there some other kind of matrix this semester that you keep hearing me talk about many, many times? And I keep saying it, it's a good thing when your matrix has this adjective. Do you know what word I'm looking for? Invertible, exactly. So an invertible matrix is like a good thing, right? Diagonalizable matrix is a good thing. So guess what? I get people that start to get those two things confused. It turns out they are not the same thing at all. So in the first group work, or in the first problem on the group work, it's going to say, give an example of a matrix that's invertible, but not diagonalizable. And keep in mind, I've just given you a little mini lecture about how to construct examples here. So give an example of something that's invertible, but not diagonalizable. And then the second part of the question is, give an example of a matrix that's diagonalizable, but not invertible, to show that kind of you can have one without the other, right? They don't necessarily go together. So let me pass this out. What I'd like to do actually is have everybody get up to the boards here and try to see if you can, with your whoever you want to work with, it doesn't make any difference. I'll give you 10 or 15 minutes to try these two problems. There should be lots of markers. I guess I don't even really need what's over here on the sidebar. I'll just go ahead and erase. Let me erase the stuff that's on the sideboard here. Grab 2 or 3 people. It doesn't matter. I don't want you working alone, though. I want you to be talking to your friends. It's good to collaborate. All right, and I'll make some room over here for you guys. Anya, do you have some partners? Yeah, you can join these guys. Absolutely. Yeah, oh, you need markers too. There we go.
Me too. Make sure just like
Okay. Write an example on the board for me if you got one. We have a whole team here. There's a group of
We
6.
gotta make sure
Yeah. So that's diagonal. Diagonal. I cannot see.
But scalar multiples of each other?
So are we just gonna look for numbers?
I think it's like.
Oh, you want to try?
Yeah,
That's
I think that's what it is.
So is there a
Like letters that say, does it?
Yeah, actual numbers would be great.
So some of this.
Either repeated values.
Okay.
So
then-
So our lambdas are.
Will you do cross? So 9 minus 10. Oh, yeah, plus.
How do you check that?
Yes. Is that triangular?
No.
No. So we're not taking advantage of my constructing examples. Now you got a triangular matrix. The determinant is not 0. So it is invertible. And then what was your question?
Oh, so can we say like since we're not scalar multiples?
No, but those
I know, like,
they
we kind of like rely on the.
Right. You're gonna actually have to look. Lambdas are very. You're actually going to have to look. You're gonna actually have to look at the null space of,
This one doesn't work.
this is gonna be A minus I. So you need to take this matrix and check it out. And ask yourself, okay, does this eigenvalue hold? This has a weight of 2. It has a weight of 2. The question is, does it give you 2 eigenvalues? So you got, and I will tell you right now that your example is a perfect example. It will work, but just these 3 you do. Understand, that's right. Yep. How we doing here, team?
Well, that one doesn't work.
It doesn't work, you found an invertible matrix, but it doesn't pull it from lambda. Good job, excellent, I love it. Anybody need help?
1 minus 6 is -5. Well, that's actually. Yeah.
You know you do it to me.
Wouldn't that make it easier?
Basically, we
Not
just need
necessarily, the
to
eigenvalue is
do 1, 2.
Let's put a 0. Okay, great, so
this would be
now you've got the determinant.
So this for sure is because
So
of
that is invertible. And you just have lambda 1, 1. Okay. Try, you guys can help them out.
That's B.
Yeah.
No, it's a 0. Oh.
Okay, so this was a 0. So another reason started with the minus.
Probably, maybe it changes.
It's not that, wait. No, this is. I know this one.
Oh wait, that's the actual number. Yeah, somewhere else. That's true because none of the.
We're here to learn. We're here to learn.
Make your matrix lambda. And I know that the lambdas are just right on the so I can actually fudge the example. So use the same lambda twice.
Alright, so I guess we can augment this with zeros.
Take a 2 by 2 matrix and see if I'm gonna get an example.
Oh no, this is actually gonna end up with 2 vectors. You know why?
It is.
You want to try and do it.
No.
Yeah.
Just like work it out. Yeah, so we got two pivots now, right?
So this one is one that's right.
One.
Yeah, you can
So that's what we
Yeah,
get.
yeah, these two are.
Well, we do end up getting a free variable.
So we get three variables. I mean,
Yes.
basically, it's two dimensional, right?
This is y.
Yeah. So we know that all that y. So we know y equals 0. That's essentially zero. Oh,
So let's say this.
Oh,
You guys don't want to.
Yeah, it's just-
I need space, so I think it's going to have space. For lambda, one.
We know this is false.
The space is for. I can say they have. That's the space that I need that, right?
Oh, yeah.
Yeah, so it's-
It was like 9:30. I was like, oh, God. If it was midnight.
Yeah.
It's just all zeros. Yeah, I was kind of sure
When you land on zero.
If you did that, then you could.
So it's invertible, but not diagonalizable. I need one too. Somebody else overriding.
You guys doing okay here? Oh, looks good. Yes, right. This does not pull its weight because it's twice here and only one vector came out of it.
No, the lambdas are zero.
Looks good. Good job, good job.
What are we doing here? So for the last one, it says A plus B equal to A. So this is A and this is B. Can you add them, just get all zeros?
Can I, this matrix is invertible.
Oh, this is B, this is A.
For one B, yeah, for one B, it's supposed to be diagonalizable, but it's not.
I know it's not. It's 2 minus 0.
Yeah, so this one doesn't be. Right, this one is invertible. This one's actually both. This one is two different lambdas and the determinant is not zero. So it is invertible.
Yeah, okay.
So
For,
maybe you can fix.
for 2B, is this
Oh,
diagonalizable?
you know what it is? It is because this is this is triangular, so I can just say that my lambdas are zero, and then my null space, you know, of A minus lambda I is actually just this matrix, and we do get to free variables. There's no pivots. We don't even have to do any work. There are no pivots, so both X and Y are free. You bust out the variables and get, so this eigenvalue does pull its weight. But I do like what you did in the sense that you have something that's obviously diagonal. Obviously diagonal.
It happens to me like 3 times.
Ended up repeating over here. So it's actually really good what you have. Like you just need to like erase a couple of numbers on that example and you'll be able to make it work. So you want to have a pivot over here so that you don't have very many eigenvalues. Anybody need help?
Because I guess I try to kill it. It was just like, okay. Because like we're going around.
No, I don't. Yeah, it's okay. Oh, so then that does get rid of zero.
And then the lambda is just be
You don't actually have to go through the.
well, the null space is already figured out.
You just need to go far enough to say, yeah, I can see that there's only going to be one variable.
Wait, wouldn't it be all zero?
I'm not gonna apply. Because I'm already. So we did.
Yeah, so we have 0 minus 0, 0 minus 0, 0, and 1 minus 1.
Wait, so lambda equals 0?
Yeah, so this one.
The first one does.
And I think for here, instead of getting zeros.
One where lambda equals 0, and then that's one where it equals 1.
Oh, yeah.
So we do null space for
Wait, so then what does that mean? And then 1 minus 0, so 1 minus
This is true.
Right, so for each corner, right, not each corner, top left, bottom right, you're effectively just putting a minus 0.
Well, then it'd be like minus 0.
Yeah, it's just gonna be all zeros.
Oh, but I want to like.
So putting that in.
No, but then this will be for sure.
Well, we have to calculate what.
No, they're different.
Yeah.
So what happens if we make like a.
Right?
Oh, maybe there's still 1 and 1. Yes. Yeah, no, 0 means it's.
Yeah.
So we have 1, 2,
So the lambda is 1 and 1 again. Make sure your parameters are all. And so we get 0, 1, 0. Anybody need help? Did that give us 1? X is free. Y is 0. Yeah. So again, it only gives us 1. If there's no now, I don't know. Yeah. Yeah. False premise example. In another situation, if you don't get any free variables at all, but you're just going all the way from, then no something's wrong. Because you yes, together. So I don't know exactly what went wrong here, but for sure, you don't actually need this to just say that it's true. Good job, good job. Anybody else need a hand?
Why?
That's it for 2A, right?
It's just one?
Okay, we have, 3 different answers. Are there any? I don't think that's. There's no reason. If you have to already know add up something like this. So this one is. You just have to say, oh, there's no repeat lambdas, or I don't think it must be. It's just that, that's all I got. Really helpful. Okay. Everybody doing okay? Were you guys able to? I think that one works. Just a second. No. And actually, I want to go back to this one. This is no longer chapter. Yeah. Did you work it out? Yeah. So you actually, see, I can't just look at it and find out. You did all this? Lambda squared minus 3 lambda. Oh, that's actually minus 2, plus 2 minus 2. Right, okay, so then you got 0.
Oh, yeah, that's.
So it's a little more work than you needed to do, but it works. I would have just done this. Because now it's triangular, and your lambdas are two different numbers.
So that's not, yeah, that's
And you determine it as 0. So you could have just put this down and then you would have. But what you would have done. Now, the problem down here is I would love to end up with this matrix because I agree that this one is non-diagonalizable.
Or like, I didn't like, oh yeah, that's good.
Okay, but neither are either of these. Because you have the same lambda. So how about we just fix it?
Yeah, make that a
So
negative
whatever,
minus
whatever
minus
number
two.
these are.
Make this a -2, and now you're golden, right? Now you've got two different lambdas here. And you've got two different lambdas here. So these are both diagonalizable. But then when you add them together, each one is now all of a sudden the lambda was a real, and it didn't.
But wouldn't it, because when it's like, this one has to be a 1.
Unless you no repeated numbers on the diagonal, then you actually do very fast. Just say, oh, it's diagonal.
So the number of things in there.
And you set this up in such a way that you end up getting these things here.
So when would it?
Now,
not
just
be
because
like-
these read this doesn't go.
It would have to be like this.
So you have to check here. But that's just.
If it was like that, or like
You're right. Great, so let me say this problem to you guys in a slightly different language. What we just shown with this example is that
What
the
if that
set
was
of
a 2?
diagonalizable
Does that mean that this one has to be 2?
No, the numbers up here.
The number up there don't correlate to this at all.
Whoa,
They
go
don't
way back to
have
chapter
don't
4.
matter.
What
It's the
did the
number
subspace
of
have to be? It had to be closer addition and scalar multiplication. This is not closer addition. Here's a diagonalizable matrix, which you added them together and ended up non-diagonal. So we can't talk about diagonalizable because it like doesn't work.
It's like that. It's already guaranteed to be diagonalizable.
Exactly.
Because it's
Okay, fantastic. I'll let you read that over. Yes, did you guys come up with
Like,
something?
maybe I'm thinking something for like, what is it?
I know, well, I was thinking, I was like, well, yeah,
But it's like, this one's already guaranteed to be.
Yeah.
So it's, you know, like.
Yeah, and then down here, I kept swapping numbers.
We did all this because we forgot about the fact that.
And so like, we just stop right
Yeah, we
there.
could just stop it.
I mean, it's in practice. For me, it's-
Yes. Yes.
You guys have any questions? I don't see anything here, but I just want to make sure you all good.
Anyone have the eraser paper?
Hey, guys, why don't we all reconvene again? I think most of us have finished the group work, maybe not everybody totally, but we did pretty good on that. Oh, you know what? I'll erase that, Carlos. Don't worry about that. I'll take care of it. I will take care of it. Luis, you know why I keep doing that is there's somebody in my other class who looks just like you and has the other.
What does the logo look like?
Sorry. It's my bad. You know why I'm having trouble this year? It's because I'm not passing that paper. I used to always pass that paper. Oh, I can easily learn the next thing. Thank you. Okay, guys, great job on the group work. Thank you for that. Don't forget that the solutions to the group works, they're all in Canvas. So if you did not finish, or if next week you forget what we learned and want to review it again, it's all up there to take another look at. But I like those problems. Hopefully that was helpful for you to practice a little bit. You guys like doing the group work? Kind of a nice, gets us up and out of our chairs for a few minutes anyway. I want to spend the rest of the first half of our class today to finish chapter 7. I just want to say a few words about why we care about diagonalizable matrices. Seems like it's a good thing when the matrix can be diagonalized. Every eigenvalue pulls its weight and so on and so forth. But what's so great about that? How does that actually help us? So there is a section that we don't need a lot of time to cover this, but I would like to do that here. 7.3, the title of this section is Diagonalization. So just continuing on the same theme that we've been talking about, this is what we're going to do right here. So just for the setup, I'm going to let A be an n by n. Let's say we have a matrix that's already diagonalizable. So it's an n by n diagonalizable matrix. Okay. What is so great about that? About having a matrix that's already diagonalizable in the first place? Well, what this means, of course, is that there are n linearly independent eigenvectors, right? So let's just write that down so we can consider n linearly independent eigenvectors. These are going to be v1, v2, ... up to vn. Okay, and of course, anytime you have an eigenvector, you also have to have a corresponding eigenvalue, right? So I'm just going to draw some arrows here. We have a lambda 1, a lambda 2, and ... over to lambda n. So we have these different lambdas that line up with these eigenvectors. Okay. So now I'd like to show you what we can do in this situation. We are going to form the matrix. We're going to make a new matrix now, guys. It's going to be called S, and it's going to also be n by n. So I'm going to make an n by n matrix S. And what I'm going to do with it is I'm going to build this matrix by just literally laying the eigenvectors into the columns of the matrix. So V1, V2, V3, and so on. We're just going to put them into the columns of a larger matrix. So unfortunately, I erased over here that example from earlier. That was my mistake. I shouldn't have erased it so fast. Forget what all these numbers were. Something like this. Whatever. We had these lambdas, and then we had, for lambda equals 2, we had 0, 1, 1, and 1, 0, 0. I just want to get this back on the board again. And then for lambda equals 4, we had the vector 5, -1, 1, I believe. So we can take these eigenvectors here and just lay them out into the columns of a 3 by 3 matrix. You might say, well, why do you want to do that? Well, let me do a little calculation for you here. I'm going to call this a note. What if we take the original matrix A and multiply it by S right now? Something cool is going to happen. All right. Namely, I'm going to put the matrix S and write it out here with its columns, V1, V2, and so on. So we have the matrix A times the matrix S. It looks like that. And if you actually multiply this out, remember how matrix multiplication works, right? You go across the rows of the first matrix, you come down the columns of the second matrix. If I do that when it's been expressed in this format, I literally will just get a V1 in the first column. And then I'll literally just get a V2 in the second column, and ... up to a Vn in the last column. So there's the result of doing the matrix multiplication. Okay, you're gonna see something cool here in a second. When I see a V1, does anybody know what I can change that to? Does anybody know what that is equal to, Sebastian? Lambda V. Do you guys remember? I didn't write it down on the board today like I have the last couple of classes, but the most important equation in chapter 7 is this one right here, right? AV equals lambda V. So we're going to do that right now. I'm going to put the AV1 is lambda 1 V1. and AV2 is lambda 2 V2. And I go dot, 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 and so on and so on and so on. The last column is lambda n Vn. Okay, so that's what we would have. And what you might notice here, guys, is that the columns are still the same as the columns of S, except that they've been scaled by those lambdas. First column has a lambda 1 in front of it, the second column has a lambda 2 in front of it, and so on. And what I'm going to show you in a moment is, I'll write it down first and then I'm going to show this to you. You can actually put the S matrix now on the left and multiply that on the right by exactly the matrix. It's a diagonal matrix, which is where the word diagonalization comes from. It's a diagonal matrix on the right of this matrix S. Maybe you don't believe me that this is how it works, so let's just do a little side scratch work. Suppose you take any matrix at all. And let's see what happens to it when you multiply it on the right by a diagonal matrix. Let's just make an example to practice on. Look what happens here. Everybody remembers how to do the, it's been a little while, we've got to multiply the matrices together. So upper left corner, we have 5a plus 0. Upper right corner, we have 0 plus 8b. Lower left corner, we have 5c plus 0. And lower right corner, when I multiply it out, I get 8d. So do you see that the matrix that we started with here, this generic ABCD matrix, the first column has been multiplied by 5, and the second column has been multiplied by 8. So that's what's going on here too. If I multiply on the right by a diagonal matrix, it has the effect of multiplying the first column by the first number, the second column by the second number, and so on and so on. Okay? And so what is this? This is just simply S on the left times what I'm going to call D right now on the right, where D is the matrix with those lambdas going down the main diagonal. It is a diagonal matrix with the lambdas on the main diagonal. Yes, go ahead.
Can you just write that as lambda times IN?
This is not lambda times IN because I have different numbers here. This is lambda 1, lambda 2, lambda 3. They're actually different values. Yeah, so we should write it out like that. Very good. Is everybody with me on this? I mean, at the moment, you probably still don't necessarily think it's all that cool, but let me summarize what we have actually just done on this middle board. The summary of what we've written down on the middle board is that we started with AS and we ended up with SD. So if you build this matrix S in the manner that we explained over here by putting the eigenvectors in the columns of the matrix, then we actually get this equation right here. Okay. I have a question for you. Can I cancel the S?
It's not immediate.
I can do it, but I'm cheating if I do, right? If I cancel the S, what am I going to be left with? A equals D. Well, nobody ever said that the matrix A started off as just a diagonal matrix. So I can't just cancel. We've never really been able to cancel matrices in this class very easily. It's not been something that's just automatic. Yeah.
It wouldn't matter even if you multiply by S inverse because it's not commutative, right? So
In a minute, I'm going to use the S inverse, but you said, and I'll show you in a second. You said something very important. You said S inverse. Do I know that this matrix has an inverse? Normally, we wouldn't know that, but I claim that this is invertible. And why is it invertible would be my question. Let's come back over here in the notes and let's add that point. S is invertible. It turns out that it is possible to use an S inverse. And I'm wondering if anybody can tell me why.
This is a theoretical point, right? This is just coming from the concept. So look at how S is created. Its columns are Li. Let's just stop right there. Does that sound familiar? When you have a square matrix, when the columns are Li, the matrix is invertible. That was actually one of the things. If you go back to the A, B, C, D, E, F, G, H, I, J, K, L, M, N, O, P theorem, right? The invertible matrix theorem, that's in the list. If the columns of the matrix are invertible, are linearly independent, then the matrix is invertible. Okay, so let's write that down here. Since its columns are Li, exactly what we wanted to say. Okay, so there is an S inverse that we have at our disposal, and I would love to use it, but I've got to be careful here. I can't just put the S inverse to cancel this S and cancel this S, right? So what I can do is I can left multiply by S inverse and get S inverse AS equals D. So if I want to cancel this S, I can by left multiplying both sides by S inverse. But notice you cannot cancel the S inverse and S here because there's a matrix in between. Or if you prefer, you don't want to solve it that way, you can instead get rid of this S by right multiplying by S inverse. And in that case, the equation would look like this. So we have sort of several versions of equivalent equations here. And I just have to caution everybody to be a little careful about like which side is the S inverse on and which side is the S on. Obviously, they're not the same in the two equations. So it's probably flashcard material here, just to really get it straight for yourself. But both of those equations are true. Okay. So when you have a diagonalizable matrix S, we're not saying that the matrix is equal to D. That is not true. But we can get something where A is similar to D, basically. There's an S inverse thing that we have to live with. But other than that, the A and the D are more or less similar to each other. Yeah, Sebastian.
Why is the S inverse on the opposing side of the D?
So this is just going to be how I'm choosing to do the algebra with this equation. From this equation, I can do whatever I want, right? Except I can't divide by S. But what I can do is I can put an S inverse here and here. Then it cancels from there, and I just get this equation. Okay. Or if I don't want to do it that way, I can put the S inverse on the right side. But I have to put it on the right side of both sides. So I can do it like that. And now I've got these canceling, and A is equal to SDS inverse. That's the algebra of it.
What if that worked?
I see.
Don't overthink. So I can put the S inverse on the left of both sides, like that, in which case it's just D here. Or I can put an S inverse on the right of both sides, like that, and cancel those. And now I've got this equation. So it works both ways, depending on which equation you're trying to get. Are you trying to solve for D or are you trying to solve for A? That's kind of a question. Oh, and I wanted to mention in the homework that you're going to be doing on this, the question is going to say, is A diagonalizable? Okay, so we do all this stuff with the lambdas and the eigenvectors, right? So that's the first part. And then it's going to say, if the matrix is diagonalizable, find S and find D. Now, what I want to point out, guys, is that that is super easy to do once you've done the work over here, right? We can actually, in fact, let's do it. Let's practice on an example. So using the matrix capital B from the lecture on Monday. So I'll put a date down on this so you can refer to it in your notes. So let's go back to April 11th. Using the matrix B from April 11th, find S and D such that S inverse AS is equal to D. Where people have gotten in trouble in the past on this part of the class, though, on the homework, is that they think, oh, so I have to find S inverse. And then I have to multiply all this out and do all the work. More than what they're asking for. Don't do it. All they're asking you to do is find S and find D. We already know that this is going to be true. So don't spend the time doing that. All we have to do, I do not need much room to write this solution. All I need to do is write down S and D. So let's do it. So how does S get formed again? To do S, the columns of S are the eigenvectors. So this is the example we're using. And the eigenvectors, let's just write them into the columns of this matrix. 0, 1, 1. 1, 0, 0, and 5, -1, 1. Now, I'm going to make a mistake on purpose when I write down D. If you think you know what my mistake is, don't tell me yet. Just think it through and then I'll ask somebody, okay? So I'm going to make a mistake on purpose, which is the eigenvalues go on the diagonal of the matrix. So the eigenvalues, according to the thing over there, the lambdas are 2, 2, and 4. So here I go. Does anybody raise your hand if you think you see a mistake here? Raylene, what do you think I've done wrong?
The 4, 2, 2 is out of order.
It's out of order. Exactly. Yes, that's exactly right. Because the first 2 columns, those were lined up with the lambda equals 2. And the last column is the one that goes with lambda equals 4. So these have to be in the right order here. So this has to be a 2, a 2, and then a 4. This is the correct answer. Okay. Does that make sense? So sorry, I'm making everybody get their necks all out of whack over here. This is what we're using. These pieces of information to build those matrices. Now, I will point out that this is not the only correct answer for S and D. What else could we have done? Sebastian.
You could switch the order of the columns and then switch the order of.
As long as I'm consistent with my switching of the order. Exactly. So I could have chosen to do this, guys. I could have done 1, 0, 0 in the first column. Then I could have done 5, -1, 1. And then I could have done 0, 1, 1. But in this case, now my D would be different, right? Now my D would be 2, 4, and 2 on the diagonal. It would look like that, right? So this is correct, and this is correct. They're both correct. They're not the same, but they're both correct. And the theory tells us that if I take these 2 matrices and I calculate S inverse times A times S, I will get D. Or down here, if I calculate S inverse and then multiply it by A and then multiply it by S, I will get D. That's what these equations are telling me. You don't have to do that in the homework. The homework's not asking you to find S inverse. It's not asking you to actually multiply anything out. It just wants to know what are the S and the D that work. Okay, does this make sense? Not too bad. Now, one last thing, and then we're going to take our break for today. You still are probably sitting there saying, so what? Right? We can find S, we can find D, we get these equations, is it true? So what? What's the big deal, right? So hopefully I can finally give you a little bit of an answer to that. So even though we can't say that A and D are the same in these equations, we can use these equations to do some calculations with A. For example, using, I'll just make a note here, using diagonalization, we can take high powers of matrices. Let me show you what I mean. What if I wanted to calculate A to a big power K? Actually, so before I actually do it, let me just point out, like, where would this come up in the real world? Let's suppose there's some process going on that is modeled by a matrix multiplication. So you do the process by multiplying by a matrix. I can give you an example. What if you have two sections of Math 250B and students are switching sections? So they're, dropping this class and going to that class, going to that class, dropping it, going to this class, going back and forth, right? Every day the rosters change between the two sections of 250B. We can use a matrix to compute how many students have gone from this class to that class and from that class to this class. We can do it as a matrix. Now, let's imagine though that the students are doing that every day, not just one day, but then there's a second day and a third day and a fourth day. Every single day they do that, we have to multiply by this matrix to see the resulting distribution of the students. So imagine that goes on for the entire semester. Let's hope not. But if for 15 weeks, right, every single day students are switching sections, right? Well, then the matrix that you need to sort of say, well, where are all of the students at the end of the semester, right? The matrix that you would need would be some huge power of whatever matrix you started from. We would want to calculate this. It's something called, this is useful for anything that falls under the category of something. I'm going to write a word on the board now. We're not going into this in Math 250B at all, but I just want to get it down there. You can Google it, or you can wait until you take your 300 level statistics courses or probability courses, because that's where Markov processes come in. These are processes that repeat over time and reflect sort of changing arrangements of objects. I have a problem I do in Math 307 where a bunch of Martians are sitting around a table and there's food on every Martian's plate. And they start grabbing and stealing from the person's plate that's next to them. And the question is, well, where does all the food go? And by the end of this, if this goes on and on and on and on. And it really involves writing a matrix to model that dynamical system. And then using powers of that matrix to be able to say what the long-term configuration of the problem is. If you're interested in that, I'd be happy to talk to you more about it in office hours. You can look this up on your own. It's a very, very well-known theory. I don't have time to really do it in this class. It's one of the things, I'd love to do it, but I just don't really have a lot of time. If for no other reason you want to understand why do I care about this section, right? I just want to at least let you know, yes, in the real world, diagonalizable matrices are beautifully important because these equations now allow me to calculate these high powers. You want me to show you? Now, this is the part that I do want you to write down. A to the K, let's use the formula in the box there. This is S D S inverse to the K. And a common mistake that people do here, I see people do it all the time, they say, oh, that's S to the K, D to the K, S inverse to the K. No, it doesn't work that way. Let's actually write it out. It's S D S inverse times S D S inverse times S D S inverse times dot, 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 S D S inverse. Right, that's what it actually is. A bunch of, there's K of those there, right? And what do you notice that I could do here with this expression? kind of pretend for a minute that the parentheses don't matter, right? So just kind of put those out of your mind. There's no parentheses there. Sebastian?
Cancel out a bunch of S's.
Okay, here I do have S's with S inverses side by side. I cannot cancel them here, and I cannot cancel them here, but here I sure can. I can cancel S inverse and S inverse and S, right? They all cancel. And what do we end up with? We end up with one S at the beginning. And then there was this big massive cancellation in the middle, but what do I have? I have a D, and then a D, and then a D, and then a D, a bunch of Ds. That's actually KDs that are all together in the middle. And then at the far, far right, I still have my S inverse. Okay. And guys, it is actually relatively easy to take a power of a diagonal matrix. So what we can do is literally, I'll put it here in the middle. We can literally, when you take a diagonal matrix to a power, you're literally just taking all of the diagonal entries to that power. So this becomes the result. The lambdas get raised to the K power here. All right. And so this is something that's reasonable to calculate. S is, what we said here. We have S. We can find its inverse. And then in the middle, we have a nice diagonal matrix that we can then just do the multiplication for. So if I want to find high powers of a matrix, such as in Markov processes, right? For a diagonalizable matrix, I can do it. Right? I can actually do this and come up with an answer. By the way, the diagonal matrix here, the book does sometimes write it this way. They'll just write diag of lambda 1 comma lambda 2 dot 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 up to lambda n. That's just a notation. So you might see that when you're looking at the book a little bit. Okay, so I know I didn't provide a fully satisfactory answer about Markov processes because I just don't have time to cover it. But this is a powerful, powerful technique in linear algebra. No doubt about it. Any questions at all on this? Everybody knows how to find the S and the D. That's the key for the homework. That's all you're going to have to be able to do. Find S, find D. These are the equations. Right here. Perfect. I'm so excited. I want to tell you, we are ready to go back to differential equations. It's been a long ride, right? To get to this point, we've spent the last 2 months just doing linear algebra, with the whole purpose now is to hopefully use the linear algebra that we've learned to handle these last 2 chapters of the semester. The best part of Math 250B is the last part, is where we're going to put everything together from the first 10, 11, 12 weeks that we've had so far. So with that as a little bit of a motivation, I guess you could say, let's take a 10-minute break, let everybody get a little fresh air. And in 10 minutes, I will be starting chapter 8. So I'll see you guys back here at about 3:18, roughly 3:18.
Oh, no, she's like. Thank you. It's not really.
I sport.
You had to work?
Yeah,
Oh.
all day.
So we're going to,
Oh, it's the Easter holiday.
yes,
That's right. I just remembered that.
but it's gonna be worse because it's all down all day, so it's probably gonna be busy. Well, hopefully it's not, because people
Yeah,
like to
people are hopefully be doing their own
maybe
thing.
doing like barbecues and
Yeah,
stuff,
yeah.
but at the same time, people love to like rather not do that and just go to
Uh-huh.
a restaurant.
That's
which
true.
is-
Which restaurant do you work?
I work at a bowling crab.
Oh, okay.
I don't know if it's just the famous Louisiana Cajun restaurant, but
Oh, okay.
it's just always busy and it's always, I always get all day shifts, so usually I have to go in at from 11, come back to like 11 at night.
Oh my God, that's
And then
exhausting. But you don't work during the week.
I don't work during the week because of this.
Yeah, you wouldn't have time.
I wouldn't have time to do any of this at
No,
all.
no, for sure.
Yeah, and so I just come back and then do bits of, well, good thing it's we do on Friday
Yeah.
or Monday, because that's how.
You'll have
when
the
something
week-
do on, I usually stay up to like maybe 3 in the morning to do like bits and pieces. of
Right,
it,
right,
yeah.
right. No, this will give you a little more time.
Yeah, definitely. Good. Yeah, let's still, everyone, the classes conflict with each other. Oh my God, I feel like I have to sacrifice one class for another.
I hate it. I hate
I
that.
just like,
Yeah.
no, I don't want
When
to.
you have to, when you have that much work to do, it's tough.
Yeah.
Well, anytime I can help, you just let me know.
Yeah. So I try to keep it an untouched price. Probably will. I might. I'll see how this semester goes. I'm just taking 3 classes. The next semester I'm taking 4.
Oh, wow. Okay,
So-
step it up a little bit.
So if I can't keep up with it, I might maybe have to switch jobs. But I'm not
Right.
sure. They pay pretty well.
It's pretty good money.
Pretty good money, but
Yeah.
I
At the
want.
same time, you want.
I don't want to. I'm gonna be spending more money if I fail this class.
Right, then you have to do it again.
Do it again.
Totally makes sense. All right, everybody. I hope that it was a good little break there. I mean, this is like a big break because we're like switching two totally different branches of math from before break to after break. So I'm kind of done with the eigenvalue, eigenvector stuff for now, but trust me, it's not going away. We're gonna need it as we get into this last part of the semester. So yeah, today is the day. We are gonna finally go back to looking like a class that's a math class. It's gonna look like calculus again. We're gonna do some derivatives and try to solve linear differential equations of order n. That's the title of chapter 8. Back in chapter 1, way back at the beginning of the year, we looked at first order linear differential equations. Actually, you guys watched some videos. Remember, for the first week of the semester, we didn't really have a class. I just had you watch some videos. Well, one of the things in the videos at the very start of the semester, before we even met each other, was I talked about the nth order linear differential equation form, which is what's in the box right here, okay? So notice what we have. We have the unknown function is y, right? Every differential equation has an unknown function in it. And I like to call it y. And I also see a term with y prime, and there'll be a term with y double prime, and so on and so on. And the highest number of derivatives that we see in our equation is n derivatives of y. That's why the order, remember the order of the differential equation is just what's the most number of derivatives that you see in the expression. So this is the way it looked. We wrote, this was written down in like one of those early videos that you guys watched back in January. The A0 of x, A1 of x, and so there's an x that can kind of be any expression whatsoever. F of x can be any function whatsoever. But this is the form, guys, of an nth order linear differential equation. And our goal is to solve it, okay? Now, you guys might want to start your stopwatches right now. And let's see how long it takes before we start using linear algebra to say something about this process. You're probably sitting there thinking, oh, we're done with linear algebra. We're never going to see it again. Well, start the stopwatches. We'll see. Not going to take long. Because what we're going to try and do is rewrite this linear differential equation using a linear transformation. Okay, so let's do this. Let's set up some notation. This is just going to make it a little easier to write this stuff down. We're going to kind of start off with just a little notation here. Sometimes I'm going to use an interval I. So capital I is going to be an interval in the real numbers somewhere. So that's just really to establish a domain for the functions that we're working on. And then I'm going to use another notation, c to the k of I. This is just the set of k times differentiable functions. That just means these are functions that you can differentiate k times, and it'll make sense in the interval capital I, right? So it'll make good sense. So these are just notations. They don't really come up very much in the primary work that we're going to be doing, but just wanted to have those there. And then we're going to now define the derivative operator. Okay, so this is a definition. The derivative operator, and this is a function that I will be denoting with a capital D. And D is a function. So if it's a function, then it's going to have inputs and outputs. So it's just going to take functions that are differentiable and spit out, well,
I'll just say C0 of I, that just means that the functions on the right-hand side don't have to be differentiable any longer. The derivative operator D, and what is the formula? Well, D of F is just F prime. So you're every time you see a capital D, it just means take the derivative. Take the derivative, right? And we don't necessarily just want to take one derivative because the differential equation has order n. So I want to be able to take more derivatives than that. So more generally, we can talk about d to the k. This one will go from c super k of I to C0 of I via d of F equals k derivatives of F. So this is just a notation, really. It's just a notation. Oh, I'm sorry, this should say d to the k of F right here. D to the k of F is just k derivatives of F. So if you see powers of D, it just means take higher derivatives. Could be something you've done in calculus for sure. But what I want to point out, and I'll call this a note for right now, is that D, not to mention D squared and D cubed and so on, D, I'll go ahead and write them all down. D squared, D cubed, and so on. All of these, they aren't just functions, they are linear transformations. Okay, so if anybody,
3 minutes, 40 seconds.
did you do it? 3 minutes and 40 seconds. That's how long it took me to get back to linear algebra again after we started differential equations. Thank you. It wasn't going to take that long. And here we are. We have a linear transformation. Okay. What's that mean? That means that these derivative operators respect addition and they respect scalar multiplication. That's what linear transformations work. They respect addition, right? So in other words, D of F plus G is the same thing as D of F plus D of G. So this is what we're saying. And same thing for scalar multiplication. So they are linear. So in fact, guys, I'm sorry, can we go back in our notes and put a star on this original nth order differential equation I wrote down? Because I want to refer to it now. What I'd like to do is I would like to rewrite star using the D notation. So we're going to want to use the D notation for some of the stuff we're going to do in this chapter. So I'm going to use the big D notation to rewrite my nth order linear differential equation. Okay, so you ready for this? Here we go. The first term on the left is A0 of X. I'm just going to write it as A0. And then we have what? N derivatives of Y. So I'm going to put the of Y part way over here on the right. So we have A0 and then D to the N. And then we have plus. The second term is what? A1 times what?
1
D to the
and minus 1.
N minus 1, exactly. D to the N minus 1. And we keep going on and on and on, dot, dot, dot. And then the very last two terms, maybe I'll do the second to last term, which is A N minus 1 times D, one derivative of Y. And then the very last term is literally just plus AN. Okay. And then on the right-hand side of the equal sign, we have a big F. The big F of X. Just write it as big F. Okay, so this thing in the parentheses on the left side is just a big grand linear operator involving the different powers of D. We're actually going to get even a little bit lazier and give that a new name. I'm going to call it L, and this L is a linear transformation as well. It's just a combination of the various powers of D in an expression that's already linear. So this will respect addition,
This will respect scalar multiplication. So our differential equation becomes, just simply becomes, this is getting very, very abbreviated now. It just becomes L of y equals big F. That's ultimately how it's going to look. What do you suppose the goal is here? What's the goal when we're studying differential equations? What do we usually want to do?
Find the family solution.
Find the solutions, right? Solve it. We'd like to solve it. So the goal is solve for, we have to solve for the unknown function, which is actually y. So the goal is to solve this for y. We have L of y equals F. And the goal is to solve that for y. And it's going to take a couple of lectures to really talk through chapter 8 as to how we're going to do that in a variety of situations. Is everybody with me so far? This is a lot of just setting it up with notation, to be honest. We haven't actually got any specific examples down yet, but are there any questions so far? Pretty straightforward. In fact, let's do an example. I think it might be, I'm not actually going to solve a differential equation yet. I just want to understand how this L thing works. Okay, so let's just do an example here to practice the operator and the notation that we have. So let's do this. Let's let L be equal to x minus x squared times d squared plus sine of x times d plus 2x plus e to the x. Okay, let's just say we have that. And let's imagine that I want to calculate, let's actually try to compute L of y. Let's compute L of y. I'm going to take a specific y here. Let's say that y is 2x plus, well, actually, let's do something different. Let's do y equals 5x plus e to the 3x. Just take that as an example. Okay. So I just want to understand how this works. I'm going to show you in a moment how to actually calculate this thing. Yes.
Wait, wasn't our goal to solve for y?
Yes.
So why do we have for y?
Because I'm not doing this yet. Okay. But I just said I'm not going to do this yet. I just want to practice how the operator works.
Okay.
Because I find sometimes people have trouble understanding exactly what L is. So this is a differential operator. It's a linear transformation. And we're going to just practice how the L works on this example. Okay, I'd like to show you guys this. Other questions so far? Is everybody okay? Honestly, the first thing I like to do is I like to say, well, how many derivatives am I going to need? And I look back over here, the biggest power of d that I see is the second power. So that would be 2 derivatives. So the very first thing I'm going to do, guys, is just work out the first 2 derivatives of my function. This is not a bad way to start. Just collect this information. So I said we're going to do some derivatives today, right? I take the derivative of 5x plus e to the 3x. So that's going to give me 5 plus 3 e to the 3x. And then if I take another derivative, I'm going to pull down another 3 in front of the e to the 3x, and I get 9 e to the 3x. Okay. And so now I can start working out L of y. It's going to be x minus x squared times 2 derivatives, so I'll just write that as y double prime, plus sine of x times y prime. And now here's one that sometimes people will forget. On this last term that's just dangling over here on the end, don't forget that that is also being applied. You can see it here. It's also being applied to y. So this has to also be multiplied here by y. So remember, the way you should think about this, guys, is you're taking this L right here, right? You're taking this L and you're applying it here to y. So it's almost like you're distributing the y to all of the terms here, right? Just like almost multiplying it out. But every time the y hits a d, we take a derivative. So here we have 2 derivatives of y
Here we have one derivative of y. Here we don't have any derivatives of y, but we still have to multiply it by that last term. Yes,
So could you just write d to the 0, just?
you could definitely do that. I'm not going to, but you certainly can. And since I've already calculated my derivatives, I'm just gonna stick them in now. Okay, so this is just going to be x minus x squared times 9e to the 3x, that's y double prime. And then plus sine of x times y prime is 5 plus 3e to the 3x. And then plus 2x plus e to the x times the original y, which was 5x plus e to the 3x. So that would be the answer. It's just nothing particularly exciting here. I just wanted to practice how the operator thing works. Does it make sense how I got all that? Everybody thinks I could do one of those if you had to? Okay. Let's see where I'm at. How am I doing on time here? Oh, I'm doing great. So if, let's go back to what Nathan said, if we are given y, we can plug it into L and come up with an answer. But that's not normally the way this is going to work. Normally, we don't know what y is. We want to solve for y given L and given big F. So that sounds like something harder. And it is harder. Actually, the very first part of the semester, when we were first doing differential equations, didn't I say at some point, probably in one of my videos, even at the end of 15 weeks in Math 250B, guys, there are still going to be tons of differential equations that we just can't solve. We just can't do it. And that is still true. Unfortunately, I have to tell you that even with all of the linear algebra that we've learned, that somehow I'm going to show you its value in a few minutes. Even with all of that, guys, there are still going to be lots of differential equations that we cannot solve. However, I would like to make some headway here as much as we can. Imagine with me for a minute that this big F was actually just 0. Okay. Somehow, if the differential equation has a 0 on the right-hand side, I'm going to hope to convince you in the next 12 minutes that it is a little bit easier to figure out the solution to the equation. So first thing I need to do is give you the name for that. When you have a 0 on the right-hand side and you take away the big F and you just turn it into a 0, that is, there's a name for that. It's called the associated homogeneous differential equation. So one more definition here, guys. This is probably about the last definition for the day. Definition. The differential equation L of y equals 0. If we throw up our hands and we say, okay, it's too hard to solve it with big F, let's just change it to a 0, right? This is called the associated homogeneous differential equation. So we just put a 0 there on the right-hand side. Okay. So we have this differential equation now. If I wanted to solve this for y, I claim it's a little bit easier because I wonder if anybody knows why. Does this look like a concept that we have learned in the linear algebra? So, you know, the L is like a linear transformation, right? The y is like a vector, like the functions that we're working on. And the right-hand side is now a 0. Have we seen this lately? Say again? It's the kernel of L, exactly right. So we're not talking about solving
some random equation with solutions that are spilled all over the floor, right? We're talking about the kernel of L, which is a subspace that has a basis and a dimension. We kind of know how big it is. That's pretty nice. It's exactly right. So to solve this, so solving this differential equation is literally equal to finding the kernel of L. The kernel of L. So there's the linear algebra showing up again, right? The kernel of L, what is that again by definition? That's the set of vectors, in this case y, such that the transformation of y goes to 0. In other words, L of y is equal to 0. So we can actually write it that way. So it sounds a little less daunting when I say, okay, instead of trying to solve this differential equation, how about you just try to find the kernel of a transformation? And we know that that kernel forms a subspace. It forms a vector space. And in fact, there is a theorem, I will not be proving this theorem in this class, but I'm at least going to state it, that the kernel of L, in other words, the set of solutions to L of y equals 0, which is the kernel of L, forms a vector space. It forms a vector space. Now, we already knew that. This is not news, right? The kernel of a transformation is a subspace. It's closed under addition, closed under scalar multiplication. We've known that since the start of chapter 6. Since we very beginning of linear transformation. So we know that that's a vector space of, now here's the new part, of dimension n. The dimension of it, now that I'm not going to prove right now, but the dimension of the kernel of L is n. What's the n again? The n is the order of the differential equation. It's the most derivatives that we see in our equation. You see, the thing about this that's really cool is that, okay, so I'm not just going to be chasing my tail trying to find all the solutions to my differential equation. No, I know exactly how many solutions I have to find in order to span all of the solutions. So I'd like to wrap up today's class with an example, which always excites me every time I present it in this class, because it really shows the power of the linear algebra to solving a problem in differential equations. Here it is. Example, find the general solution we did questions like this way back in chapter 1, right? Find the general solution to the differential equation. Here it is, d squared plus 1 of y equals 0. So we're going to focus on homogeneous differential equations. Even next Monday, I'll be mostly working just with homogeneous equations, and we'll deal with the big F later on in chapter 8. Okay. By the way, guys, for most of chapter 8, there are no matrices, there are no vectors. It's all just scales. Kind of looks like a calculus class again. Somebody could walk in here and say, oh, that must be, math 150A or something like that. I'm not sure. So it's kind of a nice break. Most people like chapter 8 as a nice break from all this crazy matrix stuff. But yeah, so this is just, what is this? If I just want to write it in the derivative notation, it would just look like this, right? Just y double prime plus y equals 0. So what I'd like to see if we can do, I'd like to see whether I've got any people out there that have maybe an idea what the solution would be. Now, next week, I'm going to give you a recipe for this so that you don't have to sort of think of it in your head. But can anybody think of it in their head right now? Can you think of a function whose second derivative, so you take two derivatives of it, and by the time you do that, you have the negative of what you started with.
Fine.
Hold on, I didn't call on you yet. Does anybody have an idea?
We're going on a linear and say sine.
Go out on a limb and say sine. Yeah, how about the sine of x? The sine of x, right? You take two derivatives of that, you just get negative sine of x, right? Exactly. So I'm just going to note that, let's call this y1 of x equals sine of x is a solution.
So e to the negative x.
Okay, hold on. Somebody that I have not heard from today want to give me another solution? Can you think of another function? Somebody I have not heard from today. I've heard from you, Who have I not heard from? Gus, do you have an idea? Another function whose second derivative is the negative of itself?
Negative of itself.
Yeah, well, yeah, so after you take two derivatives, you get the negative of what you started with. So like when you start with sine, if you take
Oh.
two derivatives, you get,
Yeah, negative cosine.
okay,
Negative sign, negative sign.
negative sign is correct, but I want to take cosine. I just want to take plain old cosine. That's another solution, right? So also, you guys, probably I give you enough time, everybody's going to come up with this. This is not the most bizarre functions by any means. So cosine of x is also a solution. Okay, yes.
E to the negative x.
E to the negative x, does that work? You take the one derivative of e to the negative x, you get
Negative.
negative e to the negative x, and if you take another derivative of it,
Negative times negative.
you get another negative, it goes back down. This is actually equal to itself again. It's not equal to the negative of itself.
Oh,
So this one actually doesn't quite work.
0.
Okay, yeah, there's lots of other solutions. But since I've only got 4 minutes left, I got to stay on track here, guys. So what's cool about this right now, guys, is not so much that we found these two solutions. We all could do that. What's cool about it is that these are actually a basis for the two-dimensional kernel of L. Look at the kernel of L. What did I say here? The kernel of L is a two-dimensional vector space. I've got my basis vectors here. Note that if I form that basis, sine of x, cosine of x, this is a basis for the kernel of L. See, here's the thing. If we didn't have the linear algebra, if we didn't know how big this kernel of L was supposed to be, we could sit here for 5 weeks looking at this differential equation thinking, I wonder if there's some more solutions. I wonder if I could take some crazy combination of, I don't know, a logarithm and a radical and a fraction. And how do I know that I can't do some crazy weird thing and come up with another solution that's not here yet? Well, the fact of the matter is, these are already a basis for the kernel of L. What's that mean? That means they span the whole kernel, right? Everything that is in the kernel of L is a linear combination of these two things, right? So what this means then, guys, is that the general solution to the differential equation. Are we ready for this? This is a big punchline, right? It's simply y of x equals any possible linear combination of these, right? So C1 times cosine of x plus C2 times the sine of x. This is the answer to the problem. That's the answer to the problem. Now, I want to make a note. I want to make a note here. This set of vectors here, I say that they're a basis. What does it mean to be a basis?
You don't understand.
Li is the, yeah, they have to be a spanning set and they have to be Li. These are Li, and I just want to make a note here. These are Li. Just make a little asterisk here. Can somebody tell me why these are Li? Normally for Li, I throw my vectors into the columns of a matrix and I look for pivots and stuff. I don't really know how to do that when I'm talking about sine and cosine. Like I wouldn't know what it means to put them into a matrix, right? It's not so obvious to me what to do. But there is a reason we can give, and I'm wondering if anybody has an idea. How do I know that these vectors are Li? There's only two of them. Yeah, Bill, Josh?
Is it because they're never equal to each other?
It's not just that they're not equal to each other, but even more than that. So for two vectors, Sebastian?
They're not scalar multiples?
They're not scalar multiples of each other. Exactly right. Since sine of x and cosine of x are not scalar multiples. They're not scalar multiples. And so the conclusion then is, so we have n equals 2, right? The dimension of my kernel of L is 2, and k, this is the k value. The k is, remember the whole k versus n thing? They're both equal to 2. So k equals n, so it's either both or neither. Remember all that good jazz that we did a while back? If k equals n, then if they're Li, then they're also a spanning set. Okay, so we have k equals n equals 2 implies, I'll just say both, going back to the way we would have said it in chapter 4. And by both, we mean a basis. The beauty of this, guys, I'll just wrap up for today. The beauty of this is every possible solution to this differential equation is right here. You don't have to go searching and searching and searching and think, gee, could we have missed something? Is there some other function that just miraculously has two derivatives of it equal to the negative of it? You're not going to find it. This is the whole bag of solutions right here. Really, really awesome. Now, in my usual soap opera style of teaching, which means I have to hook you to come back next week, right? Two quick things you might be wondering about. We're not going to take any notes on this. But one thing is, if we had more than two vectors here, we wouldn't be able to talk about scalar multiples. So the question is, well, what are you going to do in that case? What if I have 3 or 4 or 5 functions? So I'll teach you a little Wronskian trick next time. That's just an easy way to do that. That's one thing. And then the other thing is, what if we didn't come up with these solutions? What if we couldn't think of it? Right here, we had to kind of get lucky. I had to hope that somebody in the room would know two derivatives of these functions would cancel the function out. What if we don't know it off the top of our head? Next week, I'll tell you that you don't have to see those things for yourself, that we can actually do a method to derive them. So I'll look forward to that next week. But meanwhile, guys, have a great weekend. Thank you for being here today. And we will talk again soon. Office hours tonight and tomorrow. Bye for now.
Yeah.